This is Agents A1. It's a massive mixture of experts neural network released by the Shanghai AI Lab, promising trillion-parameter level performance. The accompanying technical report outlines sweeping capabilities, claiming state-of-the-art performance across 6 distinct, highly complex scientific and engineering domains. But when you clone the repository to verify those claims, you don't download a sprawling infrastructure. You receive a working tree that is exactly 121 megabytes. The repository provides a model release and a partial evaluation harness. It lacks the infrastructure of a standalone agent framework or a self-contained benchmark. Auditing this repository reveals severe reproducibility gaps, baseline comparisons of mixed provenance, and by design execution paths that pose extreme security risks to the host machine.
A clean Git history offers zero protection when the software's explicit purpose is to execute untrusted model outputs directly on your hardware. Traditional malware checks miss the primary threat vector of agentic evaluations. This diagram maps the 6 evaluation domains reported in the Agents A1 technical paper: search, engineering, science, instruction following, general agentic, and scientific agentic. If you attempt to run these evaluations yourself, you will find that exactly half of these domains are missing from the codebase entirely. The pipelines for machine learning engineering, science, and instruction following are documented in text files, but there is zero executable code provided to reproduce them. Looking closer at the remaining search domain, the reported score of 75.51 on the BrowseComp benchmark comes with a catch. The harness uses a non-standard protocol that retries a failed prompt up to 5 times while completely resetting the agent's context. Other research labs do not evaluate BrowseComp with this context reset. The reported score is not an apples-to-apples comparison with the broader industry. The authors note in their report that their baseline comparisons are of mixed provenance. The competitor metrics in their tables are an unverified blend of their own self-run data and figures directly copied from original technical reports. Researchers cannot independently verify over half of the performance metrics from the provided code. The academic claims operate separately from the reality of the release. Despite the missing components, the search evaluation harness is genuinely runnable, consisting of nearly 3,000 lines of well-structured code. It offers hardware flexibility. By setting the Agent API base URL environment variable, you route inference to a remote endpoint, completely bypassing the need for local GPUs. This flowchart illustrates the architecture of the multi-turn React loop. It starts with an LLM call, parses the requested tool, executes that tool, appends the result to the context, and feeds right back into the start. The loop operates under strict caps. If a run hits a 150-minute wall clock timeout or reaches a 128,000 token limit, the harness forces the agent into a sudden state, demanding its best answer immediately. During the execution phase, the agent has access to 3 specific tools: Google Search via the Serper API, web page reading via Gina, and a Python interpreter running on a self-hosted Sandbox Fusion server. Once the loop terminates, the harness evaluates the agent's success using an LLM as a judge protocol. The judge models are hard-coded per dataset, assigning GPT-4o for the Gaia benchmark and Gemini for Xbench. Because this scoring protocol relies entirely on paid, closed-model APIs and live web fetches, the grading is inherently non-deterministic and will drift over time. While this is a robust reference implementation of a deep search agent loop, the sheer volume of LLM calls, automated retries, and judge API requests creates massive financial exposure and sets the stage for severe execution risks. From a traditional security standpoint, the repository is clean. There are no malicious setup files, hidden binaries, or stolen credentials buried in the Git history. The true threat vector here is by design execution risk. The benchmark's core function is to execute unverified code generated by the LLM. This code snippet from the MatTools evaluation suite reveals the first critical vulnerability. On line 84 of utils.py, you will find a Python eval function. The harness uses this host-side eval command to parse NumPy array expressions directly from the model's output. This creates an immediate, unsandboxed code injection path right on your machine. Mat Tools does include a Docker sandbox, but the implementation is porous. The containers default to full network access, run as the root user, and lack any CPU or memory limits. The Molebench evaluation path contains a far more severe vulnerability. Deep in the run script, the code constructs a system command utilizing the flag dangerously skip permissions. This script builds a Claude CLI command that intentionally disables permissions and executes it via a subprocess, directly on the bare metal of the host machine, bypassing container isolation entirely. Furthermore, this Molebench path routes the agent's traffic through a local capture proxy. While intended for telemetry, this setup can log request bodies and expose your Anthropix API key in plain text. Evaluating deep search agents essentially turns your own machine into the primary attack surface. Running this suite without strictly engineered protections is practically suicidal for your local system. To safely run the search harness on a standard 8-core CPU machine, we must define a strict quarantine protocol. First, avoid installing the default requirements text file. It unnecessarily drags in a massive VLLM and CUDA stack designed for hosting the 35 billion parameter model locally. This diagram maps the secure deployment architecture. Start by isolating your runtime inside a boundary box, utilizing a slim Python 3.10 virtual environment, installing only the necessary routing dependencies, like QuenAgent and LightLM. From there, ensure all inference is strictly routed out to a remote OpenAI-compatible API endpoint. This completely offloads local compute and prevents untrusted waits from executing on your hardware. To safely handle the Python execution tool, spin up the Sandbox Fusion server inside an entirely separate, heavily fortified Docker container, restricting its access to the host machine. These are the final security mandates. Always deploy inside a dedicated, throwaway virtual machine. Employ strictly scoped, budget-capped API keys, and absolutely never run the Molebench host-side Claude execution paths. The Agents A1 repository is a legitimate and valuable reference implementation for deep search agent loops, but extracting that value requires treating the framework with rigorous zero-trust infrastructure protocols.